Okay. Uh, uh, we started the section 2, norm spaces. Okay. The first definition in this section is the definition of a norm. What is the norm? Uh, let X be a vector space and let X be a vector space over field F, and a norm on X, a norm on X is a function like this, from X to R with the following properties. For X and Y in X and scalar alpha, we have these properties. The norm of X is non-negative. I mean, it is positive or zero, and this is zero when uh, this is zero only when X is zero, and the norm of alpha X is I don't know why my electrical pen doesn't work. Uh, Unfortunately, it doesn't work. Okay. Please ask for microphone again. Someone wanted to speak, but I couldn't uh, allow him. Please ask again for microphone. Okay. Okay, I can work with my pen. So we have these properties. The norm of x is non-negative. It is positive or zero, and it is zero just when it is zero. And the norm of alpha x equals the absolute value of alpha dot the norm of x. And this property is a triangle inequality property we call x and the norm and norm vector space. As you see, a norm vector space is a space with a norm. So as you see in B, a vector space X on which there is a norm is called a norm vector space. Or just a normal space. Unfortunately, it doesn't work. I don't know why. Something must be wrong, I don't know. Okay. So B, as we said, a vector space X with a norm is called a norm vector space, or simply a norm space. C, if X is a norm space, a unit vector in X is a vector with the norm 1. If there is a vector with norm 1, we say that vector a unit vector. Everything is okay? You should wait. Okay. The internet is not good, it's weak here, unfortunately. And sometimes there is no internet. Okay. Example. For example, if f equals r or c, a field, the function from f power n to r defined by this. The sigma of xj, the absolute value of xj power 2, and all the sigma power 1 over 2 equals the radical of the sigma of the absolute value of xj power 2, j from 1 to n. This is a norm, and we call it a standard norm on Fn. So when we say a standard norm or Euclidean norm, we mean this norm. Here the dimension of Fn equals, there wasn't voice for a second, so I should share my screen again. Now I think everything is okay. Okay, you have my voice and the picture. Okay, I explain this example again. Let the function norm from Fn to R defined by this, the norm of x1 xn equals the sigma of absolute value of xj power 2 and all the sigma power 1 over 2. This is a standard norm on F. So when we say that a standard norm or Euclidean norm, we mean this norm. Here the dimension of x equals n. Now let x be a finite dimensional vector space over F, and E1, E2 until En be a basis for x. For any x in x, we can write x equals the sigma of lambda j ej, j from 1 to n for unique lambda 1, lambda 2, lambda n in F. For any x, there are unique lambda 1, lambda 2, such that we can write x equals the sigma of lambda j ej. The function norm from x to R defined by this, the norm of x equals the sigma of lambda j, absolute value of lambda j power 2, and all the sigma power 1 over 2. This is a norm on x based on the basis E1, E2, En. So for example, if x equals R3, a three-dimensional vector space, and the standard basis for R3 is IJK. Now we can write a vector V as xi plus yj plus zk, and the norm of V by this definition equals x power 2 plus y power 2 plus z power 2, and all this power 1 over 2. Okay. Another example 2.4. Let M be a compact metric space and CFM be the vector space of continuous f-valued functions. Means the functions that are continuous from n to f. And the domain of these functions is M. Now the function from CFM means the such a vector space 2R defined by the norm of f, the sup of all f of the absolute value of all level f of x for x in M. This is a norm on CFM called supremum norm or a standard norm on CFM. Here is the reason of why this is a norm. So you see that there is it is written solution. Solution is the reason of the of why this is a norm. So for example, if we want to verify the solution of this example, we should show that this function has the property of norm. For example, I, the norm of f, that is the supremum of the set of all absolute value of fx for all x in M, this is non-negative. The first properties of norm. And if this supremum equals 0, f must be 0 for all x, so f equals 0. And other properties are verified in this solution. Okay. Another example that is important is for a measure space x sigma mu. In a measure space x sigma mu for p from 1 to infinity, the norm of f is defined the integral over x of the absolute value of f power p d mu and hold this integral power 1 over p. This is a norm on LP of x. Again, it is called a standard norm on LP of x. If p equals infinity, as you see, the norm of f infinity is the essential soup of the absolute value of f of x for all x. This is a standard norm on L infinity of x. You may solve these norms in function in real analysis 1 or real analysis 2. And here is the solution, but I pass the solution. Another example is a norm on L, small l power p. A small l power p is consisting of all sequences xn. So capital L power p of x consists of function, measurable function on measure space, but here LP for small l is the all sequence xn. So the norm of such a sequence is defined by this, the sigma absolute value of xn power p, and hold the sigma power 1 over p. This is called the standard norm on LP with a small l. For p equals infinity, the norm of this such a sequence xn infinity is the supremum of the absolute value of xn for all n. This is a norm on L infinity. So we have LP when p is not infinity from 1 to infinity, and a norm on L infinity, L power infinity. This is also a standard norm on L infinity. They are examples of norms. There are some other examples. Example 2.8. When we have two normal space, we can define another norm on the Cartesian product of x and y. So let x and y be vector space over F, and let x be the Cartesian product of x and y, x cross y. Z will be a vector space, and we can define a norm on Z by this equation. The norm of order pair x and y is defined as the norm 1 on x and norm 2 on y. We suppose that norm 1 is a norm on x and norm 2 is a norm on y. So we can define a norm on the Cartesian product of x and y. A lemma. In this lemma, we define a metric on a normal space like this. Let X be a vector space with a norm. Now we define D from X cross X to R by this definition. D of X and Y equals the norm of X minus Y. So by this definition, X and D is in this space. For proving this lemma, we should show that the D of X and Y defined by the norm of X minus Y has the properties of metric space. The first property in A, you see the D of X and Y equals the norm of X and minus 1. It is non-negative. And the other property B, D of X and Y, if the D of X and Y equals 0, the norm of X minus Y must be 0, and it is 0 if and only if X minus 1 equals 0, and it happens if and only if X equals 1. So the D of X and Y equals 0 if and only if X equals 1, Y. This is another property of metric space. And we can prove the other properties like this. I write for a study, so please study the proof of this lemma. Notation. If X is a vector space with a normal space with a norm, and D is defined by D of X and Y equals the norm of X minus Y, so D is called metric associated with norm. So we call this metric a metric associated with a norm. If we change the norm, the metric D will be changed. So this D is related to the norm. Again, we should wait for internet. Okay. Okay, another example. For Fn and Cfn Lpx L infinity x, we can define by a standard norm a metric associated with the standard norm like this. For example, for Fn, the metric D associated with a standard norm is the norm of x minus y, and this is equals the sigma of the absolute value of xj minus yj power 2 and whole the sigma power 1 over 2. And for CF, when F and G are in CF, D of F and G equals the norm of F minus G, and this is equal to the supremum of the absolute value of F of x minus G of x for all x. And the other standard, the other metric space with a standard norm are like this. Please study C and D by yourself. Now we have a theorem. Let X be a vector space over F with a norm, and Xn and Yn be sequences in X which converge to X and Y respectively in X. And let the sequence alpha n be a sequence in F. So we have A, the absolute value of norm X minus norm Y is less than or equal to the norm of X minus 1. B, the limit of the norm of Xn equals the norm of X. You see, when Xn approaches to X, the norm of Xn approaches the norm of X as well. The limit of Xn plus Yn equals X plus Y, and the limit of alpha n Xn equals alpha X. Here is the proof of the theorem, but we leave it to you to study the proofs. Now there are some exercises. I will send you the solution of some exercises, not all the exercises. I choose some exercises from any chapter and solve them, and I will send it, the PDF of them, to you by WhatsApp. In this section, we are going to study finite dimensional normal spaces. When we say finite dimensional, spaces, we mean that the dimension of X equals, for example, n, when n is not infinite, is finite, less than infinity. And X is a norm space. So there is a norm on X, and the dimension of X is finite. Definition. This is an important definition. I write important. Let X be a vector space and norm 1 and norm 2 be two norms on X. Two norms on X. Any vector space can have many norms, sometimes infinite norms. So we want to say when two norms are equivalent. If there is, for example, norm 1 and norm 2 on a vector space X, we say that norm 2 is equivalent to norm 1 if there are two positive number m and n, capital M and a small m. When we have these inequalities for any X, m of norm 1 X is less than the norm 2 of X, and this is less than or equal capital M dot the norm 1 of X. So the norm 2 of X is between two norm of norm 1 of X. Because the equivalent, when we say norm 2 is equivalent to norm 1, we can say by changing m and n that the norm 1 is also equivalent to norm 2. So we can say that they are equivalent simply. So we say that these two norms are equivalent. Now we have this lemma. Let X be a vector space with two norms, norm 1 and norm 2 with 3. In fact, with 3 norms. Norm 1, norm 2 and norm 3. So we have 3 norms on X. Let norm 2 be equivalent to norm 1 and norm 3 equivalent to norm 2. So norm 1 equivalent is equivalent to norm 2. It means that if two norms like norm 2 and norm 1 are equivalent to one norm like norm 3, they are equivalent to themselves too. So if norm 2 and norm 1 they are equivalent to one norm, here in fact norm 2 is equivalent to norm 1 and norm 3, because norm 2 equivalent to norm 1 and norm 3 equivalent to norm 2. So norm 1 and norm 3 are equivalent to norm 2. So norm 1 is equivalent to norm 2. No, it's not. Okay, it means that as I said, if norm 2 is equivalent to norm 1, norm 1 is equivalent to norm 2, 2. They are symmetric. Equivalent of norms is symmetric. And 3, norm 2 is equivalent to norm 1. Here we can say that because norm 1 and norm 3 are equivalent, both of them, to norm 2, so they are equivalent to each other. I left the proof for your study. Okay? Our class must be 1.5 hours. But I just teach 1 hour because I know that you will be tired, but not less than 1 hour. This is the minimum time for class. Normally we should be in the class 1.5 hour. But as I told, because I know you will be tired, I teach only 1 hour, but not less than 1 hour. So we start 4 o'clock Iraq time to 5 o'clock Iraq time. Okay? I remind you that we have every week 4 o'clock Sundays. This is our fixed class, but for Tuesday we have every other week. I mean, for example, this week we have session, the next week we don't have session at Tuesday. But every week we will have session at Sunday. Sunday class is our fixed class. Okay? So next week we have just at Sunday class, and we don't have at Tuesday class. Okay? So, okay, I finish the class here. And please remember the number of the pages we finish the class. So maybe I ask you where is the lesson, and you remind me the page of the lesson. Okay? Thank you too. So please remember the page of the here is page 40. Page 40. Okay. So if there is any question, please ask me. homework really. It's just for yourself, and I will send the solution to you. But please try to solve it by yourself first, and then when I send you the solution, you can compare your solution with the solution I will send you. Okay, so if there is no question, I finish the class. Goodbye. Goodbye.